try another example. Let's say we take an integral, this is going to be a definite integral, from 0 to pi on 6 of sine x over cos squared x dx. Again, an antiderivative for this is not forthcoming just by staring at it. It's not obvious at all what function I took the derivative of to get to this state. Right? But I do see a relationship between sine and cos. I know the derivative of cos is negative sine. I know the derivative of sine is cos. So maybe, it wasn't in this particular section, maybe I would start thinking about u substitution already, because I know that cos and sines have derivatives related to them. So I said you should try to find a place where it looks like there's an inner function, like a composition. So right now what I see is that cos has been put inside the squaring function. So my first guess is to use cos as the substitution, u equals cos x. If that's the case, then what I need to find the derivative of cos hiding inside here somewhere. And this one's pretty obvious, right? If I take the derivative of cos, I'll get negative sine x dx there. Again, like in the last problem, first you take the derivative and move the differential over, but you're going to do that every single time. There's no reason to write this step separate from this. Just go ahead and move the dx over automatically. So du equals negative sine x dx. Now, do I see this kind of expression here? I certainly do. I see sine x dx right here. I understand I'm missing the negative, but I can always compensate for that. It's not a big deal. So what I'll do is I'll shift the negative over to the du. Negative du equals sine x dx. All right, so if I start to replace the pieces that I see here with the variable u, it should be that I have the integral of, well, the cos x became u itself, so this is u squared in the bottom. Now above, what do I have? Well, the sine x dx, right? Sine x dx product here, sine x times dx, it's supposed to become negative du. So I have negative 1 du. Now this negative 1 I can just move to the outside. So I can rewrite this as negative u to the negative 2 du. All right. Now there's another important thing that comes along with this definite integral. That is, I need to do something with the limits of integration. These are x values right now. We don't write it, but really what's going on here is this is x equals 0 going to x equals pi on 6. We know that because the variable is x over here, right? dx is changing from 0 to pi on 6 in some sense along the x-axis. So here where I've changed everything into the variable u, I've transformed the integral into a different variable, I should also transform the x values here, the limits of integration, into new limits of integration, which are u values. So what you do now is you run these values through your transformation, through here. Right? So 0 in here for x, you cos of 0, which is 1. Okay? So the lower limit of integration goes from becoming 0 and generates the value 1. Okay? When I put pi on 6 through here, cos of pi on 6 is root 3 on 2. So therefore u is root 3 on 2 if x is pi on 6, and therefore my upper limit of integration is root 3 on 2. Okay. Let me just carry that along here, root 3 on 2. All right, so now these are actually u values, and once I find the antiderivative in u, which will be negative, power goes up by 1 to u to the negative first, and then I multiply by the reciprocal of the new power. So that is going to contribute another negative. It's going to be 1 over negative 1. So what I'm going to do instead is just annihilate this negative here. Okay? I don't really need it, it turns out. They're going to cancel each other. So I get u to the negative first, evaluated 1, evaluated root 3 on 2. And what this does, this saves me a little bit of time. If I did not change the limits of integration from x values to u values, Well, first of all, I couldn't even put anything here. If I put x values here, it'd be a little bit strange because these are u values, and I'm be putting 0 pi on 6, which are x values. It wouldn't make a whole lot of sense for the integral. But what it's really doing is saving us from transforming u back into cos x and then reusing these values from the beginning. I don't need to do that because I've already changed them into u values, so I can leave this as u, unlike what I did here. When I just had a simple antiderivative for an indefinite integral, I changed everything back to x because the problem started in x. But here I'm just trying to find the number that this integral evaluates to. I don't need to change everything back to x. It's not necessary. I've transformed it into u. This integral here is exactly the same value as this integral, so changing back to x is totally unnecessary and not really advisable as well. So rewriting this is really 1 on u. So I have 1 on u evaluated root 3 on 2 and 1 and subtracted. So 1 over root 3 on 2 minus 1 over 1. Well, that's just the reciprocal of root 3 on 2, so I get 2 on root 3. So 2 on root 3 minus 1. If I rationalize 2 on root 3, and we'll get 2 root 3 on 3. And if I write 1 as 3 on 3, I can now combine them together. So we get 2 root 3 minus 3 all over 3, and there is our answer. Yeah. Again, this is the exact same answer if you leave 0 and pi on 6 how they were, and if I changed u back to cos x to the negative first, or 1 over cos x, with 0 and pi on 6 in here. But it's usually more burdensome to do it that way, and it's better in general to get used to transforming your limits of integration into new limits of integration for the new variable.